Our title today is the law of effusion. And let's begin with this scenario. You're going to have a great big party. And for that party, you want to have a whole bunch of helium balloons. And you'd like those helium balloons to be covering the ceiling when your party begins. And so the question I have for you is, would you buy those balloons the day before the party, or would you buy those balloons the day of the party? I think we all know we'd buy those balloons the day of the party. Because if we bought those balloons the day before the party, when we woke up in the morning on the day of the party, where would the balloons be? They would be on the ground. Why would they be on the ground? What's going on with that? Hence, people, effusion. All right, so this is a flask. And in this flask, I have a gas. Like any fluid, liquid or gas, if I uncork this thing, if I take the top off, this gas will go all over the place. And we call this phenomenon diffusion. Okay, so this is diffusion right here. And both phases of fluids do this, liquids and gases. They will randomly distribute themselves in terms of as much space you give them, if it's a gas anyway. And what we will find is through this random distribution, it appears that they're going from areas of high concentration to lower concentration, because they're just mixing up so that everything's homogeneous. Okay, so this is diffusion. Random. Random spreading out of either liquids or gases to areas of, from areas of high concentration to areas of low concentration. Okay, this is different from effusion. Now what I'm going to do is I'm going to make a little container. And it has a boundary here. And right in the center of that divider, there's a little teeny tiny hole there. And here are particles of gas. And when we speak of effusion, what we mean are these gas particles escaping through this little tiny opening. So that's what effusion is, okay? So effusion is the movement of a gas through a little tiny porous opening. So Graham's law states that the rate of effusion of a gas is inversely proportional to the square root of the mass of its particles. So let's put this into a mathematical formula. We would say then the rate of one gas compared to the rate of effusion of a second gas is equal to the square root of the inverse of the ratios of their molar masses. Inverse. Square root. MM equals its molar mass. Alright, with any good law, we know that there's going to be some mathematical problems that are associated with them. So let's do some mathematical problems associated with Graham's law of effusion. So the first thing we might see is calculate the ratio of the effusion rates of hydrogen gas to uranium hexafluoride. Alright, now the first thing we're going to need for this is we need our mathematical formula of rate 1 over rate 2 is equal to the square root of the molar mass of 2 over the molar mass of 1. And so just because it makes it easier in the end to compare one to another, because it doesn't really matter. We're going to put our lower molar mass as 1 and our heavier molar mass is 2. So we're going to say the rate of H2 over the rate of uranium hexafluoride is equal to the square root of their molar masses. So the molar mass of uranium hexafluoride is very large because of that uranium. 352.02. Okay, this mistake is going to get made, people. Don't let it be you. Okay, remember, we're doing the inverse of what we've done here. Divided by 2.02, that is the molar mass of hydrogen. Okay, so what we're going to do, we will divide these, find their square root. You should probably do that on your calculator just to make sure you're doing this correctly. And we get an answer of 13.2. And what does that mean, 13.2? Well, that means that the rate of hydrogen effusion is 13.2 times greater than that of uranium hexafluoride. So our ratio here would be 13.2 to 1. So for every 13.2 hydrogens that can effuse through a little tiny opening, 1 uranium hexafluoride will effuse. So for every 13, approximately, we will get 1. Okay, so that's one way that we can look at this. How else will we be asked to do problems about effusion? It took 4.5 minutes for a liter of helium to effuse through a porous barrier. Porous meaning that it has little tiny holes. Tiny holes, like a balloon. how long would it take for 1 liter of chlorine gas to effuse through that same barrier? If it took helium, 4.5 minutes. So, what we will do, again, is we will say the rate of helium versus the rate of chlorine gas is equal to the square root of the molar mass of chlorine, which is 70.9 divided by 4.00. And so what we get here is 4.21. So another way we can look at this ratio is that it's going to take the chlorine 4.21 times as long to effuse as the helium. Helium is 4.21 times faster. So this is what we're going to do. We're going to say, well, 4.21 and then our time here took 4.5 minutes for the helium, and it's going to take the chlorine 4.21 times longer. So our total amount of time is what? You solve that, and we'll look at that tomorrow in class. All right, so, of course, smaller the molar mass, the faster the effusion is going to be.